Okay, we have started recording. Okay, so we had left a couple of few theorems to identities to prove last day, but before that, I want to point out the last thing that I said yesterday was a bit incorrect. So I had said that A transpose and you would append an I below. So if you are already taking A transpose, you will just do this, right? For finding the row space, I mean the column space, because once you take the I transpose, A transpose, you're initially you had rows, right? R1, R2, dot, Rm, which will be A transpose will be R1, R2, dot, Rm, right? So here you would be ending up with your C1s here, C2, Cn. You would essentially be having C1, C2, and so on, like Cn. So your same law, same process that you apply to get the augmented elimination for the null space of A transpose will also hold for the null space of A and the column space of A, right? You will augment on the right hand side only. You will be eliminating rows. Otherwise, you will have to do something like this: A comma I and do elimination on the right. Right? Then what we said will hold, because we will take linear combination of the columns and convert them into a null space like this. Just think about it. So if you're already converting the rows into columns and columns into rows, you can find the column space using the same definition as you used to find the row space, right? Okay. So let us do few one only these two are important. Other two are other all are very simple, just application of simple things. So what does it say? So it says that the sum of two, the rank of sum of two matrices is given by this identity where it's the sum of the rank of each individual matrices. So after subtracting the joint rank of the this R means the column space here, column space. So instead of writing R, let me just put column space of A intersection column space of B. Okay. So wherever you are finding, so let me just keep that. I don't know. Let's keep, because I've written this notation everywhere. Let's not mess with it. So I have written R because R is called the range space also. Range space, also known as the column space. Both are the same. So in case I write row space, I will write row of A or R of A transpose. Okay, just the notation. So how do you think I'll be showing this identity? What step should I do? So remember, we had done something like x plus y as a sum of two subspaces, right? So bx, let us say, is the basis of x. So let us write, instead of writing this, let us write what will be this set. We had, remember, we did something called a direct sum and all. So this will be the intersection of, so say we will be proving this theorem for the time being. X plus y is equal to dimension of x, and then I'll show you how is it related to the first theorem, where x is a vector space. Okay, so can you tell me what to do? how to start with this? Do you see it is similar to a set equation? So if I take a set like this, bx intersection by, and write z1, z2, zk, what is the dimension of bx intersection or x intersection y then? K, right? So x and y were the two subspaces. They are defined by basis of x is this, basis of y is this. So do you agree that bx is a superset of bx intersection by, or span of whatever? Yes or no? So this is the intersection of two sets, and this is just one set. So A intersection B is always a subset of A, right?
Yes. Yes.
So how will I make Bx using B intersection Y? Any idea? From B, this set, how will I get
B
the?
intersection by union bx.
No, but I need to construct a Bx. Say you already have Z1, Z2, and say this Bx dimension of B is, or dimension of X is, say some K plus L. So I already will have Z. I will already have a ZK, right, which is part of B intersection by. Yes or no?
Yes.
And I can add some extension set to this to complete the entire all the basis vectors.
Yes.
And then similarly, I can do that for Y also, right?
Yes.
Y, say P. So your dimension of Y will be K plus P, right? So what will be the dimension of X plus Y?
K.
No, X plus Y will be sum of two spaces we had done yesterday, remember? So what spans X plus Y?
X union Y.
Yes. So Bx union By, right? These two span X plus Y, yes or no? We had shown yesterday. Sum of two
Yes.
subspaces is the union of their basis vectors. So this is equal to Z1, Z2 all the way to Zk, and X1, X2, XL, and Y1, Y2, Yp. So the dimension of X plus Y will be K
K plus
plus
L plus P.
P. So see now, so your K plus L plus K plus L is dimension of X, and P is dimension of Y minus dimension of X intersection Y, right? So, but is my proof done here? So, is my proof complete? Like, do you think that this is a valid proof? So everything is all right over here. No, but we have already shown yesterday that X plus X union Y. No, we have to show one thing that is left. Tell me what we have to show. So I have shown that this is valid, right? So this is a valid basis. Do you agree? Bx and by are valid basis, right? Yes or no? So, but anywhere that I've written Bx union intersect union By, does this guarantee to be a valid basis? Have we ever shown that it will be a basis? It can be a
No.
superset of a basis.
Yes.
It can also be a superset of a basis. If it is so, we have to show that Bx union is minimal. So span test 1 is done. Span is yes. And what is test 2? What we'll have to do is they are independent, right? We'll have to show that they are independent also. So how will I show that they are independent? Anyone? So we have to show the set Bx union By is independent. So recall, how do I show they are independent? So then
the linear combination is equal to, not equal to.
So we'll be proving by contradiction. Let's say they are dependent. Okay. So alpha I zi plus beta I xi plus say gamma I yi. This is what the set is. L and this is I equal to 1 to k, right? So now you see. So these two. So your x zi's, right? For example, so alpha I zi, you can write this as what? Okay, you have this, right? Alpha I zi I equal to 1 to k plus beta I xi equal to minus gamma I yi. Now tell me something. To what subspace that this belong to? To which space does this belong to?
Y.
So you're using these, right? Yi to yp, yes or no? You're using a subset of these basis vectors. So of course it is a part of your, right? Belongs to y or not?
Yes.
Similarly, this set, what is a subset of? C. So your zi and xi is the basis of x, yes or no? Z and x together forms the basis of x.
Yes.
So this should belong to x or not?
Yes.
Okay. So if left hand side belongs to x, right hand side belongs to y, that is not possible, right? Until and unless they both belong to what? They are non-equal subspaces. So if they a vector that is belonging to both of them must be in the intersection or not? Is this clear? So this is belonging to LHS is belonging to your x. RHS is belonging to y. So but if you have to equate them, both should belong to the same subspace or not? This is one vector v1. This is one vector v2. So you cannot equate vectors which are not even in the same subspace. They will never be equal, right? So think of a plane, and these vectors will be, one will be this side, one will be this, one will be this side, like this. So they can never be equal until and unless they are in the intersection, right? I hope this is clear. So if it is in the intersection, so what can we write this as? Do you agree? Can I write this as some delta I zi's? Yes or no? Intersection is 1 through k, this set.
Yeah.
So if a vector belongs to this intersection set, they'll be belonging to the linear combination of its basis, right? So the linear combination of the basis is Z1 to Zk's linear combination. So I'll get gamma I yi I equal to 1 to p is equal to 1 to k delta I zi. Right? Equal to 0. Do you agree? By equating these two. Right? So now what are yi's and zi's? They are the basis for y. Yes. So do you get the contradiction? Basis for y. So must be independent. Independent. So your delta I equal to alpha I, your gamma I is equal to 0. Similarly, you can show alpha I is equal to 0 and beta I equal to 0. By combining the other two, right? If you combine this and equate with x, you will again get beta I is equal to 0, right? Yes or no? If I was combining the first two initially. Next, I will combine z and y. I'll start with by and come to bx. Did you understand? And then I'll get all these will be 0. So bx union by is independent. So is my proof done? So my proof is done, right? So how will I relate this to this? So x can be written as a matrix. I can write x as a matrix or a column space of a matrix, whatever you want to write, right? What is rank of A plus B? What is rank of A plus B? Dimension of column space of A plus B, right? So this is some space. Agreed? Which will be equal to rank of column space of A plus rank of column space of B minus rank of minus dimension of column space of A intersection column space of B. So this is nothing but rank of A plus B. This is the right hand side is again, so dimension. So I'm taking to take dimension throughout. So dimension of rank of A plus rank of B minus this, right? Understood? How did I get from the dimension equation to the dimension of the column space equation?
Yes.
Others, are you not following? So let's do something easy first, and then we'll go to the second question. So just to show that you can understand. So let us try this. Similarly, this you can try as your homework. Same approach. So can you tell me how will I show range of AB is a subset of range of A? Very simple. This we have already shown yesterday. Rank nullity equation. This also we have shown. In the last class, that the number of rows, independent rows is always equal to number of independent columns. By elimination we showed. Can you tell me row of AB, how to show that it's a subspace of row of A? So say, so what do you understand for showing this? You have to show if X belongs to range set of AB, X will belong to range of A. If that is true, then this is true. You have A as a subset of another set. What does it mean? If the subset is holding, the superset will also hold or not? Say A is a subset of B. A holds. True. So will B hold or not? So A is somewhere here. So B will also hold.
Yes.
So how will I show that? Say X is in the range space of AB. What does it mean? From yesterday's, if you recall what we have done yesterday. So X can be written as AB times Z, right? Yes or no? If it is in the range space, what does it mean? There exists a Z such that you can take the linear combination of the columns of AB. What is the range space? It's the column space of AB, right? I don't know what happened. Yesterday, everybody was understanding everything. Today, nothing. So for a matrix A1, A2, AN, Z1, Z2, Zn, what does it mean? Summation of AI, Zi. Yesterday I showed you that how to take the what is a vector matrix product. So does it belong to the column space of A or not? If this is some L matrix, so Lx, do you agree Lx belongs to the column space of the matrix?
Yes.
So any vector matrix product will give you a vector which will belong to the column space of B. Understood?
Yeah.
Okay. So now, so if this is true, this is also true. X is equal to A BZ by the properties. I'm just taking a associative. I can multiply this to make a vector and then do it with A. Right? So what is BZ? Does it belong? Yeah, tell me. Huh?
Some vector y, and then we can show
Yeah.
that it belongs
Y
to
belongs
A,
to the Y belongs to the column space of B.
column space of B. Yes.
Correct. So you can write A summation of Zi Bi, right? If B is equal to B1, B2, and so on. Right? So now this is also equal to Zi or Bi A Zi. Right? Where does A Zi belong to? Column space of A, right?
Yes.
So this set belongs to column space of A or not? We are taking linear combinations of vectors in the column space of A. So by the property of a subspace, it will also be closed. It will be closed, right? By property of subspace, closed under linear combination, right? So we have shown that it belongs to the column space of A. Therefore, the range space of AB will be a range space subset of range space of A, right?
Yes.
Okay. So this one you try. Let's do. So these two are same questions. Let's do one of these. Other one you can try. So tell me, how do you show that the dimension of A plus dimension of the range space of A transpose is equal to N? So I have to show number 7, dimension of null space of A plus dimension of column space of A transpose is equal to n, right? How will I show this? So use a theorem that we have already proved yesterday. How can I write?
So
yeah,
dimension of n minus a is what? M minus
okay,
r.
n minus, yes. So good. So
And
we have
then
already seen by elimination that this is true. This we have proved yesterday. So what is rank of R? This is, what is rank? Nothing but dimension of, tell me.
column of A transpose.
Whatever,
Column of
right?
A.
Right? Row space of A or
Column space of A.
column space of A transpose, or whatever you want to write. So rank is always equal to dimension of range space of A, which is also equal to dimension of range space of A transpose, right? So you have already told me that. So I will just take this side. So I'll get dimension of null space of A plus this one I will put dimension of range space of A transpose is equal to n. Similarly for M, you can put what? You can use the null space of A transpose, right? So if you're using dimension of null space of A transpose, this will be equal to M minus R, right? Similarly, you can prove dimension of null space of A transpose plus dimension of range space of A is equal to M. Now, why is it so interesting? That's what I'll show you now. I'll show you this picture that the row space and column space and null space are orthogonal spaces. What do I mean by that? That every vector in the for all x belonging to null space of A and for all y belonging to the row space or column space of A transpose y transpose x is equal to 0, right? Okay, let's see. So if a vector belongs to column space of A transpose, what does it mean? So let us write. So X belongs to null space of A. What does it mean? How can I write it as an equation?
Ax equals to 0.
Ax is equal to 0, right? Then what will I do? If y belongs to the column space of A transpose, what can I do? Tell me. So if y is in the column space of A transpose, how can I write it? So there exists a z, right? Such that A transpose z is equal to y. Yes or no? So if it is in the column space of this, so this is true. So now I have this equation and I have this equation. How do I go about showing that y transpose x is equal to 0? Any idea? So I have this over here. So this is also equivalent to saying y transpose is equal to z transpose A. Yes or no? Right? Yes or no? I'm just taking transpose on both sides. Correct? Then next step, I will multiply both sides by x. So I'll get y transpose x is equal to z transpose ax. What is ax? See. So do you agree y transpose x is equal to 0? So y is perpendicular to x. Right? Understood? So you have something like this. So you have a matrix A, which is say m cross n dimensional. Right? So if a matrix A is m comma n dimensional, what is the dimension of the null of the so what is the row space a subset of? Row space is a subspace of how many dimensional subspace? Row space is a subspace of correct Rn. So this is why this equation is interesting. And similarly, you will agree that null space of A is also a subset of R to the power n. Yes or no? Because you will multiply this with a vector which is n dimensional 1 2 to get equal to 0. Both are subspace of R to the power n. So if I add these two, at most, what is the dimension I'll get? This is why I was showing you null space of A plus row space of this will be always equal to n. This is another way of showing it, right? And since they are perpendicular, it will be a direct sum. Yes or no? So see, so I have shown that the row space, this is your column space of A transpose is orthogonal to null space of A. Yes or no? So whatever spaces you have, so this is one space, this is another space. These two spaces are orthogonal. Do you agree? Am I not able to explain? And this point will be 0, 0 or just a 0 because it's a vector. Right, I have shown this result, right? A row space and the null space are orthogonal. What does it mean? That the intersection of these two spaces equal to 0, right? If they're perpendicular vectors are independent. We'll show it. But remember from your class 11 and 12, so whenever you had perpendicular vectors, you could not take component of one to the other. So they were always independent of one another, right? So you tell me what doubt you have, or we'll go to the next today's session. We have completed whatever was left.
Brother, could you explain this null of A subset of Rn and how they are compared to each other, the row space?
Yeah, that's what I'm saying. So first result, did you understand that the row space and the null space are orthogonal?
Yes.
So this picture you understood?
No.
If they're orthogonal, what does it mean? Two spaces being orthogonal means that if I have a vector here and I have a vector here, what will be the angle between them? 90 degrees?
Yes.
So the spaces themselves are 90 degrees separated, yes or no?
Yes.
This much is clear. Don't think about the dimensions now. Is it this clear?
Okay. Yes, yes.
So what is this a subspace of? Column space?
R to power n.
R to the power n. And what is the subspace of what is the null space subset of?
Also R to power n.
R to the power n. So say the dimension of null space of A plus dimension of column space of A transpose, right? Is nothing but equal to dimension of null space of A union column space of A transpose. So this result we showed just now. Yes or no?
Yes.
So dimension, so this is, or you can just put a sum. The sum of these two spaces is equal to the dimension of each minus the intersection of each, right?
Yes. 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 Okay.
So what is this? 0, right? There's not a single intersection vectors because they are perpendicular.
Yes.
So this is your 0 vector. So you get null space of A plus the column space of A transpose will span the entire R to the power n. Do you agree? Since this is 0, this will be a direct sum. And we have seen why is it a direct sum? So because we have already seen this is equal to n minus R. Agreed or not? And this is equal
Yes.
to R. This is how we have defined these two spaces. And we have also seen that they are equal to 0. So this will be equal to n. So this is what I'm trying to say. So this will be a R dimensional subspace. And this will be a n minus R dimensional subspace. So when you add these two, you will get n.
N dimension.
Exactly. Similarly, can you tell me what will happen what will happen to these two spaces? Then please try the two homeworks where I've given you. You will understand. Try. It will be just you'll write it nicely in your copy. So if you have a row space of A, do you agree? Similarly, it will be, or rather range space of A, which is nothing but the column space of A, will be equal to the null space of A transpose, right? The other two, just taking complement, you will have the same results, follow without loss of generality. Because anywhere when you are doing A transpose can also be written as A, right? Like or some matrix B. Yes or no?
Yes.
So what will this be a subspace of? R to the power m, right?
Rm. Yes.
So you have column space is a subspace of R to the power n m, and similarly I showed you yesterday when you multiply on the left hand side, you can get a left null vector. So this will also be a subspace of R to the power n. This will be m minus R dimensional, and this will be R dimensional. So understood? I have also given this exercise to you to show that the range column space and the null space of A transpose are a perpendicular. Try that. I will not give this in your assignment, so you can post it on the chat. Because it's a simple thing. You have to just redo this and convince yourself. So that brings us the end of this one. So today will be a very short one. If you stay with me, this shouldn't take more than 1 hour 20 minutes from now. So let's see if you understand and we can go faster. So today we'll be dealing with projections. So we have shown yesterday. I will just try to introduce the intuition between. So you remember, right? So when you took a vector in school, you projected this by, what did you do to project this vector to this vector?
Dot product.
So you took a dot product with the unit vector, right? Right?
Yes.
Or x cap, your unit vector. This gave you this magnitude, right? This is the definition of, by definition, this is because by definition dot product is v this cos theta. So it is like looking from the top and seeing how does it, what shadow does it subtend on the ground. So this is equal to 1. So this is equal to v cos theta, right? Just taking the projection as Hussein was telling me yesterday, right? So v cos theta and r cos theta, r sin theta. This is all we were used to do. Remember? Now, can we do it for r n-dimensional spaces is my question. Can we project two vectors in n dimensions? Not in
Yes, we can. But we would
yes.
need more number of variables.
Yes, because that you'll automatically get. You'll not get. We have yesterday. Do you remember we defined y transpose x as the dot product of these two vectors, right? So exactly the dot product because you have y1, y2 dot 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 yn and x1, x2 dot 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 xn. This is nothing but summation of xi, yi, right? So this was what we used to do in school as a dot product, summation of each component of the vector, product of the each component of two vectors as a dot product. Okay, this is trivial, I think. So with that said, how can I project B to A? Come on, someone tell me. What should be my steps?
We take the dot product of B and A and divide by magnitude of A.
Okay, that is okay, but I don't know. So I am given A, I have given a B. So I am telling you, can I make a matrix? Make a matrix P such that PB will be equal will belong to the column space or column space of A, or will be equal to some lambda A, right? So I want to project this onto the space of A. How do I do that? And for a vector, it is just that vector, right? So if I will do a orthogonal projection, right? No other option other than that, because that's how I defined my dot product, AB cos theta as the perpendicular. So do you see this is if we name this as an error vector, as Ritik was telling me, what is the length of this? Say the length is
Root over
some
of b square
x.
minus e.
That is true. Or we can say we are scaling A by some x cap, right? This is some scalar, right?
Yes.
So there is some scalar such that this is holding, right? So do you agree x cap A plus E is equal to B by sum of two vectors? This is one vector. This is your other vector. This is equal to the resultant vector, right?
Yes.
So your error vector is B minus XA, right?
Yes.
So now what will I do? So I will do something like, do you also see A transpose B minus or A transpose E is equal to 0? This is why I was taking a perpendicular projection. So I can equate it to 0. Right? E is perpendicular to A. That's how I have defined it.
Yes.
So what will I get from here? A transpose B minus X cap A equal to 0. So I'll get X cap A transpose A equal to A transpose B. This is the number. A transpose A is a number. If you do not follow, I will just stop. So this is right. This is the fraction. This is what you're telling, right, Kondar? Ritik, you are telling me this, that you will take the dot product and divide by the magnitude. Or Hossein was telling me, I don't remember. Right, so this will be this is the factor that you will scale A by. So A x cap will be A transpose B by A transpose A. Do you agree?
Yes.
And if I write this as sum by PB, so my idea was to project B onto A, right? This is a projection matrix. Matrix of B onto A, right? Of any vector, any B, but A is fixed, right? So what will I get? P is, by comparing these two, A transpose by A
By A
transpose.
transpose A.
So can you tell me what will be P square without computing it? P square B. It should be you should be able to see it from the picture without calculating. What should be P square without even, so B will help you to understand. So let's see. So P square means projection of this. Do you agree? Projecting after projecting B? Yes or no?
Yes.
So this is also equal to PB. Yes or no? I'm not sure.
Yes.
Because once I project here, so if I keep on projecting onto the same vector, I will only be left with this. I will not decrease or increase. Yes or no? So once I have projected this, once projected, this is useless. So P square has to be equal to P from the geometry. So if this is holding from this is the property of a projection matrix. So does it hold for this? So let's see. P square is equal to A transpose by A transpose A into A transpose by A transpose A. So you get A transpose A and you have A transpose A. Both are numbers. A transpose A is a number, right?
Yes.
And if you are not following, so numbers can be cancelled. So you are left with A transpose by You may be thinking, what is the difference between these two? Can you tell me what is the difference? This is a rank
Multiplication
1
of
matrix.
Oh.
Yes. Why is it a rank 1 matrix? I'm just introducing it now only so that you do not forget. So why is A transpose rank 1? Can you tell me? So A transpose is something like this. A1, A2, let's say you have A3, right? 3 A's. What will it be? It will be A1, 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 A2, A1, A3, right? So first you'll be scaling this with this, right? You'll be using this to scale it. Yesterday I had shown you how to do that. So you'll be having the scaled version of a row because you have a single row only. So your row operations will be just A times R1, right? Similarly, it will be A2 times R2 or R1 again. So this will become A1 times R1, A2 times R1, and A3 times R1. Yes or no? Where R1 is equal to A1, A2, A3. This is how we had seen row operations and column operations, right?
Yes.
So you tell me, if I have this, so I will have the same rows, like there only one independent row or not. So these are
Yes.
all will become 0 if you multiply by A2 by A1 and subtract.
Yes.
This will also become 0. So you'll be left with only R1 and 0. So this is a rank 1 matrix. Remember that A transpose will give you a matrix where the rows will only be scaled versions of each other. And that will be scaled by itself only. The vectors by itself. Let's remember that. So, okay. So this was not useful. So I told people, so I'll give you the first introduction to machine learning today. So machine learning would be just the same thing. So you have, so yesterday I had told you, so if you have a lot of equations, right? In machine learning, you have a lot of training examples. So you have a lot of equations. So you have x1, x2, x3, say your number of houses, number area of your house, number of rooms in your house, and so on. And your y vector that you want to predict, or b here in this case, is the cost. Right? So you have three variables and n very, very larger than 3, or m very, very larger than 3 equations. So how many solutions can this have? Most of the time this will have 0 solutions, right? Do you agree? Because I consider that the first 3 are independent and I get a pivot. So I'll be left with, if I have rank 3 over here, I'll be left with all these zeros. Agreed? So I'll be able to solve for ax equal to b with only 3 variables, 3 values of x, and it must hold for all these values. I told you to do this yesterday. So whatever values you will get, so if you do elimination, right? So if you do elimination, your b's also have to, I'll give you an example, then you'll understand. Okay, so let's see. 1x1, x plus y, or x1 plus y1, x2 is equal to 1, x1 plus 2x2 is equal to 3, and, or let's say take a easier example, x1 minus x2 is equal to 3, and x1 plus 2x2 is equal to 6, right? Okay. So if I solve only these two equations, what will I be left with? X1 will be equal to 2 and x2 will be equal to minus 1, right?
Yes.
So does this hold for this equation?
No.
So similarly, you can see by same, this was my question yesterday. Since I showed you all those first case where m was less than n equal to r, you can formulate in forms of ranks also. So if you put it here, no solution. So most of the times you will have no solution. Why? Because your b will be what? Outside the column space of A. So your b has to be written in terms of ax, right?
Yes.
Yes or no? So this has b must belong to the column space of A to have a solution. So there will be no, b will not belong to the column space of A most of the times. Do you understand now this thing? This is the first machine learning question we'll be doing. So we'll be trying to learn these variables x1, x2, x3 in some way, or this vector in some form. How will I do this? This is my question. So I'll show you in last week of our sessions that you can do it as a minimization problem of a least squared. So you will be fitting a line such that y equal to mx plus c, and you will be taking the error y cap minus y whole square and minimizing it over m comma c. Right? You'll minimize the error. That is your objective, to minimize the error. You want this line to be fitting these points as best as possible. But how do I do it in a linear algebra form of a way? Any idea? So if you have a machine learning form, you will be by calculus also you can do that, but by just linear algebra also you can find that. So as I told you, B will be outside the column space of A. Agreed?
Yes.
So do you see if I can project? So this is going to be my error that I am showing over here, right? If I can project it onto This space, like I have done, am I done or not? Is this the minimum error? Perpendicular distance from the plane?
Yes.
Correct. So how will I do it? Any idea? So this will be some vector on the column space, yes or no? Some v will belong to the column space of A. Correct?
Hmm.
So how can I write V as? If it is in the first, instantly when it's in the column space of A, you should be able to tell how can I write V as. You should be able to tell this. I have told this a million times now. Yeah, tell me.
V belongs to AX.
V is equal to AX. There exists a
Yes.
vector X such that V is equal to AX, such that you can take the linear combination of the columns, right?
Yes.
Linear combination of the column. This is why I have first thing I told you is to see matrix of vector and vector matrix product as linear combination of columns. There exists an X such that V is equal to AX. Now tell me. So let's write it as X cap or X tilde as I've written here. There exists an X tilde such that V is equal to AX. Now again, I can do the same thing. Do you agree that V times, or rather E times E transpose or whatever, A1 transpose E is equal to 0? Similarly, A2 transpose E is equal to 0. And say you have A has n equations. A n transpose E is equal to 0. So M cross n matrix. Do you agree or not? So A, given A is A1, A2, dot, 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 An, M very, very greater than n. Yes or no? Again, if it is not clear, ask me. I want you to think why it is true. So these AIs are in the column space, right?
Yes.
So if it is in the column space, any vector that is perpendicular to the plane will be perpendicular to them.
Yes.
So this vector is perpendicular to the plane itself. The simple 3D geometry of class 12. So if it is a vector is perpendicular to this plane, it will become perpendicular to all these vectors on the plane. So I can say A transpose E will be equal to 0, right?
Yes.
For all these elements. So what can I write E as? Can you tell me? What
Null
is E?
space of A.
No, I wanted it in a closed form. So I have already told you I want to find AX cap such that it is equal to V, right? So that it minimizes the error. Yes or no? I want to find this vector V such that it minimizes such that V plus E is equal to B. Do you understand? I want to do something like this. So what will you have? V plus E is equal to B means E is equal to B minus V, which is equal to B minus AX tilde. So I'll just put it here. B minus AX tilde equal to 0, right? A transpose B minus A transpose A, X is equal to 0. Or you can say X tilde is equal to A transpose B into A transpose A inverse. Hoping given A is full column rank. This we have seen yesterday, that M greater than N equal to R. This case I had shown. The other case I had shown, I told you to do this, right? Where I told there will be no solutions. So there will be an inverse will exist if it is true. A transpose A. What is the dimension of A transpose A? So which step is not clear? Is this step clear?
Yes.
this step, then this is just distributive property, and then this is taking the inverse. A transpose A x tilde is equal to A transpose B. So if I take the inverse, I'll get A transpose A inverse A transpose B, right?
Yes.
So if I write AX will be equal to V. So this will be equal to, this is your projection matrix. So V is equal to PB, where P is equal to A transpose A transpose. So is A square or P square equal to P? What is P square here? P square is A transpose A inverse into A transpose A transpose A inverse A transpose. What is this? So you get A transpose A and A transpose A inverse. So what will it be? Is this P or not? So it is a
Yeah.
valid projection matrix, right? So I hope this is clear, but one thing is not very sure. So does this inverse exist? How can you say if an inverse will exist or not exist? What will be the rank of A transpose A? So for this, I forgot to do that question. Let's do it here before we go on to that. So I told you, right, that does the inverse exist? Inverse will exist. My claim is inverse exists if m very much greater than n equal to r. For this problem, don't even need, right? So n has to be equal to r. That's my claim. So I have to prove one equation that we had not done in the previous session. That is this. That is rank of AB is equal to rank of B minus null space of A into range space of B, right? Okay, let's see. So rank of AB is equal to rank of B minus rank of null space of A intersection of range space of B. So how do I prove this? Any idea? So you have understood the projection question, right? So once you're able to project, hoping that the inverse is existing, you can do this, right? So do you see A transpose A is a square matrix? Properties of this square matrix. So A transpose is n cross m. A is m cross n. So this is equal to m. Yes or no? So there's a question of inverse, right?
Yes.
So I am telling if this is true, so I will get this from here. So if it is full column rank, so my question I was saying that I have all the pivots over up to here, and then If I have all the pivots up to here, these rows will be dependent, so I'll get zeros or not. And my question would be, for this case, what is going to be, is there going to be an inverse or not? Okay, let's see. So how will I start with this? I did this question, the first question I did today was like this only. How did I do that? That dimension of x plus y is equal to dimension of x. I did that question, right? Plus y minus intersection. Here also you have an intersection. So what is the first step I should do?
We make the basis of the intersection. Assume the
Yes.
basis.
So this is equal to dimension of range space of B, right? And this is equal to dimension of range space of AB, correct?
Yes.
So we will take, say, a basis vector B as equal to Z1, Z2, Zk, and we'll take span of B equal to null space of A intersection range space of B, correct? Right? So I'm saying this space is being spanned by B. I hope it is clear. So what is the dimension for our construction? That is equal to K, right? Should not be rank, it should be dimension. Yes or no? So dimension of B would be, or null space of A intersection range space of B would be equal to K. Do you appreciate this? If yes, let's do the next part. So what should I say? I will say my other people here would be the range space of B, right? The range space of B, do you agree? The range space of B is a subset of both the null space of A and the range space of B is a subset of null space. What am I saying? Yes or no? The intersection set will be a subset of both the sets.
Yes.
Others? So it's the intersection. Intersection is always a subset. Anyways, so what will I do to get the basis for my? So instead of writing B, let me write S. It will be easier because I will be writing B for the other one. Okay, so what would be the basis? Say B is the basis of range space of B. So what will it be? So B, I can construct it as Z1, Z2, Zk, and say X1, X2, or write small b1, b2, bl. Yes or no? Right? This is an extension set as I defined.
Yes.
So I had this as your S, and this is your B, which is us. We have shown is a superset. So to go to this, I have to add some basis. This is what I have done. Next, what will I do? Any idea? What should be my next step? So AB into Z. To which space will it belong to? Belongs to the range space of AB. Yes or no?
Yes.
Good. So what is AB into Z? So I can write AB into Z as A into BZ. Correct. So this is your, this belongs to the range space of B or not? This
Yes.
belongs to the range space of B. So I can write this as summation of alpha I zi's plus summation of beta I bi's. Yes or no? This is your basis vector.
Yes.
Now A alpha is zi. What is this 0? Do you agree? And you will get summation of A beta I B into this. Yes or no? Correct. So why is this 0? If you are following, I will not tell. Why is it 0? From B, I have been able to write this. Now I have to tell me why is A zi 0? Why? Array the zi's are in the span of S, right? So S is a spanning set for the null space intersection range space. So these are in the null space of A or not? Zi's are in null space of A or not?
Yes. Yes.
So by definition, I have defined them as in the intersection, spanning the intersection set. So I will be getting beta I A bi's. So you have how many of these? 1, 2, L of these. So am I done? A, B, Z. So what is the dimension of this? The dimension will be, so how many spanning? So your A, B1, A, B2, dot, 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 A, B, L. These would be your spanning vectors. Yes or no?
Yes.
So how many are there? So dimension of rank of range space of AB is L dimensional. Intersection is K dimensional. And B is K plus L. So is it matching? So this is K plus L, this is L, and this is L. Matching? Array, what am I writing? This is K by this definition, right? It matched. But have I really solved it? For the reason I want to complete the proof, I did not go to the technicalities. I did not show it that time. So, but have I really completed this proof? Can you tell me what is left to be done? So I have shown that ABI's span AB or the range space of AB. Correct? I have shown this. But have I shown that ABI's are independent? No, right?
No. Yes.
So that means that I haven't shown that they're bases. So I cannot write the dimension as the number of them. I hope you understand that. So I have shown this I haven't shown. So what will I do to show this? What should be my step? So say if they are dependent. So what can I write? Beta, there exists a gamma I, A, B, I equal to 0 for all I. Yes or no? Contradiction. If dependent, so there will be a solution that will become equal to 0. I hope it is clear. Next, what will I do? What will I do now? So I'll write A outside and B gamma I bi I equal to 1 to L. So what space does this belong to?
B. The
So,
column space of B.
so it belongs to the column space of B. Right? So where is it? So it is equal to so you have to show that so A comma this Z, which is in the column space of B, is not equal to 0. So how will you show that? By Zi's. So let me just check. Where is it? Yeah. So BIs. So you have all these BIs which is in the column space of B. But we have said that have we made any claim that they are in the null space of B or not? We haven't. Of A.
We know that they will not be in the null space of A because all the Z which are in the null space of A are already in S, which are Z1, Z2, and Zk.
Really? No, it's not true. Why do you know? It is not true because we have, where is it? Yeah. So we have written S as the intersection set, right? Of null space and the, the range space of B. So there can
Oh,
be
okay.
more vectors in the null space which can that can be B, right?
Yes.
So we haven't yet shown that. To show this, to show that, you have to do something like this. So have we taken anything to be in the null range space of A or B? B we have. B we already have. But we have to just let me write it properly, then I'll be able to do it. So where is it? This vector, are they independent? I'm just writing it here. I can do these things a bit lower. So is AB1, AB2, dot, 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 ABL independent? How will I show that? So I'll be using this rule. So I'll be using summation of let them be dependent. So there exists a beta I, ABI, which is equal to 0. Right? So what does this belong to? So we know that this belongs to the. So I'm just missing one thing. I'll have to. So this is going to belong to the independent are independent. So okay, now I get it. Good. So you see A times summation of beta I BIs, right? Equal to 0, I'm saying. All right. So they can be. So what is this BIs? What can this be written as? So I can write this as 1 to L of these, right? So I can also write these as, since this belong to the range space of B, right? So since this belong to the range space of B, what can I write this as? So range space of B, I can write beta I, Bi is as what can I write this as?
Some vector y or some.
I can write this as, one second, I don't know what I made mistake. Xi will come up. So I have this Zi's. Okay, as some delta I Zi plus some alpha I Bi. Yes or no? This I can write. So this is the bit. This belongs to the range space of B. What is the range space of B spanned by this one, right? Yes or no?
Yes.
So what am I going to get? So I'll get summation of beta I minus alpha I Bi's minus summation of gamma I Zi equal to 0. This is what I'll be getting, which means that since alpha and beta, this is not going to be 0. So alpha I equal to beta I equal to gamma I will be equal to 0. Since by definition, this is a Bi's and Zi's are bases, right? Since by definition Bi and Zi's are basis vectors, so you'll be having this in the you will be having this in the, or there is even a simpler way. Can you tell me what? Can you tell me? This is a I may have missed that. There's a much simpler way to do that. So this is all going to be 0. So anyways, so you will be getting that all the, since this is 0, so beta I equal to 0. So you will have A, Bi's are independent. You have, what we missed is, since this is actually in the range space of AB, also the null. So if it was in the null space of AB, what could you have written this as? So this is what we missed. We could have done it in one line instead of doing this. So this is so cumbersome. So what we missed is, I was also forgetting, we also missed. So if A into 1 into L beta I Bi is equal to 0, then what does this have to belong to? Any idea? If this is equal to 0, it has to belong to the null space of A or not?
Yes.
So what can I write? So if this is some Z, so I equal to 1 to L beta I Bi is equal to some Z. What can I write this as if it is in the null space of A? And also in the range space of B also, right? Yes or no? Because this is a linear combination of B's. Correct? Yes or not? So summation of beta I Bi belongs to some Bx. So this can be written as some Bz. Yes or no? See that, see this. You're taking linear combination of this, where these are the basis vectors. So this, you can always get a for the B vector, a vector Z, such that this is going to hold, which is a linear combination of its columns or the basis vectors, right? So if this is in the intersection of these two spaces, what can I write? This will be equal to I equal to 1 to K alpha I Zi. Yes or no?
Yes.
What does it mean? I equal to 1 to L beta I Bi minus I equal to 1 to K alpha I Zi equal to 0. When will it be equal to 0? Look at this. This is a part of a basis, right? Right? It is only 0 when
All are 0. Alpha 1 and
is
beta.
it? Yes. So we'll just delete this cumbersome procedure. Will not. This is not required. So what steps did I follow? I had missed that. Sorry. So what did I follow? I said if this is some Z, right? And AZ is equal to 0. So Z is in the null space of A. Yes or no? Z is in the null space of A. And also, since beta I, Bi's belong to the range space of B, do they belong to the range space of B? Here? Yes or no?
Yes.
Not clear. So we can write 0 into Zi's plus I into. Now it is clear that it belongs to the range space of B. Yes or no?
Yes.
No, it do you, if you have a doubt, tell me. So I was confused. Sorry I confused you. So do you agree Z belongs to the null space of A intersection range space of B? So it
Yes.
also belongs. And then what did I write? So I'm going to write, since this is true, I wrote this step where I wrote Z is equal to some alpha I Zi, because this belongs, Zi's are in the intersection of these two spaces. I hope that is clear now. Okay. So we have proved this theorem, which says that rank of AB equal to rank of B minus dimension of this. So can I use this to show that A transpose A is equal to the rank of A transpose A is equal to rank of A? Can I prove it? Use it to prove that? Now I'll stop for 1 second. If anyone has a doubt, you ask me, or then I'll go to proving that. Hussein?
No, sir, it's clear. Yes.
So did you understand where I went wrong?
More
What?
or less, yes.
Yeah, that's okay. So let's see. So this we are trying to prove rank of A transpose A is equal to rank of A. How will I prove this? Very simple.
We have to show that the intersection of null
Yeah.
of
So
A
this is rank. Yes.
is 0, basically.
So just recall what rank of A transpose A is. Rank of AB is rank of B minus rank of or dimension of null space of A intersection range space of B, right?
Yes.
So I can write rank of A transpose A is equal to rank of A minus dimension of null space of
E transpose.
Intersection range space of A. Have we already shown that this is phi? The null space of A transpose and the column space are perpendicular. Yes, just in the previous section we saw that.
Yes.
So this will be 0. And rank of A transpose we have already seen equal to rank of A. So did you see that inverse exists? So you can be asked in your ML interviews or something like that, does your linear regression always guarantee a solution? So it only guarantees a solution if you have a full rank, right?
The intersection is 0, no? The origin is the intersection, which is why the
Yeah.
dimension is 0.
Yes. So intersection is just the phi. The dimension phi means this. The okay. You're saying yes. That is true. I wrote phi. 0 is something. Yes, correct. Sorry. So that's why you have a 0-dimensional space. Correct. Okay. Now today we'll start off with what is known as eigenvectors and eigenvalues. So before we see what is an eigenvector and what is an eigenvalue, all this while we had taken linear combinations of vectors to convert them into the column space, right? So this is only for square matrices. All these solutions will be only for square matrices, right? So this is a solution to this problem. Ax is equal to lambda x. What does it mean? Graphically, it means that if you have column vectors and you have this eigenvector, so you take the linear combination of the columns with respect to this eigenvector to stay in the same line or the same direction. Do you understand? So for a square matrix, the column space and the row space are both n-dimensional. Remember, right? So if you have a vector x, you multiply the vector x with a. So what are you effectively doing? Taking ax is ai xi, right? So you get lambda x. What does that mean? It means that your x vector does not change in orientation. What it does is only scaling. Okay, and why is it useful? We'll be seeing. Is this idea clear? So your vector x still remains the same. You multiply a with say a vector 1, 2, you may get back 2, 4. Right? It's going to be same in same direction. Is it clear? Do you want me to go to the motivation behind why we need this, or do you want me to explain the geometry more? Okay, since no one is asking anything, so we'll go to the motivation. So see, in optimization that I'll be showing you eventually in hopefully in 2 weeks time, 2 sessions time. So you may be told to solve this quadratic equation with a constraint, which is x transpose ax. Do you agree x transpose ax is a number? It's a single scalar because this is a vector, n-dimensional vector. This is a 1 cross n-dimensional vector. Right?
Yes.
So if I take the derivative like this, what will I get? I'll get ax minus lambda x is equal to 0. Right? So this is a simple quadratic. Think of it as ax square minus lambda 1 minus x square. So if you take derivative with a vector in this case, you will get 2ax minus lambda x is equal to 0. That's what I've written. So for this type of a equation, you will be left with a solution that is a eigenvalue eigenvector solution. This is one case in optimization, you need this. Another case is, as I was telling you, for difference equation or differential equations. I'll show you the difference equation case. See, if you have a Fibonacci sequence, for the Fibonacci sequence, what can you write it as? Say the kth term can be written as like this: k plus 1 term can be written as k plus k minus 1th term, right?
Yes.
I can also write another equation just to make it a vector matrix equation. Fk plus 1 is equal to fk plus 1. Or rather, let's write fk equal to fk. Okay, so now what can I say? I can say fk plus 1 fk is equal to 1 1 1 0 fk and fk minus 1. Yes or no? I can write this way. Right?
Yes.
Okay. So now my question is, if I can find, say this is, we start off with, say this we name as uk plus 1. You name this as uk. So if I write uk plus 1 is equal to sum a times uk, right? I'm writing this in this form. So how, if for kth solution, finding this multiplication hundreds of times would be so difficult, right?
Hmm.
So, but if I can write this uk as some eigenvector eigenvalue equation, what does it mean? So I have two basis vectors independent of them. So I can write uk in terms of two basis vectors, yes or no? A two-dimensional vector can be written in
Yes.
terms of two basis vectors.
Yes.
So if for these two, if I have ax1 is equal to lambda 1 x1 and ax2 is equal to lambda 2 x2, now you see, or this let it be u0. Do you see the benefit now? So u1 you can find like this. U1 will be equal to au0, which will be nothing but equal to c1 ax1 plus cx2, right? Which will be
Yes.
nothing but c1 lambda 1 x1 plus c2 lambda 2 x2, right?
Hmm.
Now if I want to find I 100, so this will nothing but be a 100 u0, right?
Yes.
Or say I want to find nen. So do you see, you will get c1 lambda 1 to the power n x1 plus c2 lambda 2 to the power n x2. Because these will only be scalars. Lambda 1, lambda 2 are scalar values. So you are, since you are staying in the same dimension, you can find it in O1 time complexity instead of doing all this matrix multiplication. Think if it was a 100 dimensional matrix, if it was a 1000 by 1000 dimensional matrix, just knowing the eigenvalues will do it in seconds, which would take you years to complete in other ways. Is the motivation clear?
Hmm.
Not clear fully. I understand. I get it. So I wrote the first equation as u0 as c1 x1 plus c2 x2. And then what I went on to do is, I told you now, uk plus 1 is auk. So u1 will be au0. Similarly, u2 will be,
EU1.
yes. So u2 will also be equal to au0, which will
Yes.
be a square u. So
Yes.
un will be a to
A
the
to the
power
power
n
n into
un,
U. UN.
u0. So similarly, so you will just going to take the power of this scalar values, which is what very simple operations.
So
Anyways,
basically, instead
yeah.
of doing matrix multiplication n times, we
Hmm.
are converting that into eigenvalues and then doing that.
Exactly. You are going to convert into eigenvalue, eigenvector. and you will be just getting this any solution you want in instant order. So linear system of differential equation also will have the same solution. So this was the idea. Now this is a part of your optimization numerical analysis things. So but here we have to learn what are the properties of these. So how do you think we'll be finding the eigenvalues? We have to compute them, right? So computing them, you may have seen in your college or may if you have not. So we can just take it this side, right? A minus lambda I into x will be equal to 0, right? So determinant of, so this is a singular matrix, has null space or not? Has null space. And x belongs to the null space of A minus lambda I. Yes or no? So for all the eigenvectors belong to the null space of A minus lambda I. Clear?
Yes.
So what will be my determinant of a matrix that has a null space? That has a null space. We'll see that will become, if you have a null space. So if you do row reduction, what will you be left with? So I told you yesterday, finding determinants. You remember from your school days, you can do the same row reduction in determinants as you can do in as we did in matrices, and the determinant remains the same.
Yes.
So I can convert a determinant into a diagonal matrix like this, diagonal order like this. And if it is null space is 0, what will happen? I will get a 0 at the end, right? As we discussed yesterday.
Yes.
And then the determinant will be the product of the diagonals, determinant of A, which will be equal to 0. This is the idea why the determinant is 0, right? You'll be using the row reduction as you used yesterday. And then you will see that you will have a 0 as we discussed below, and then we'll get a product of the diagonals, which is equal to 0. Very simple thing. So let's do a, so formally we can write determinant as determinant of Ti minus A as product of all the eigenvalues. What have I written here? It will become clearer eventually, but as we go further. So these are known as the eigenvalues. So why are these known as the eigenvalues? We are going to see now. And this is known as the multiplicity of the eigenvalue. To be specific, algebraic multiplicity. So how many times does the eigenvalue repeat itself? That's the idea. So let's validate this for n equal to 2, and then you will understand. So let's take a matrix A as A11, A12, A21, A22. What is determinant of T minus AI? What have I written? AI, Ti minus A. So this will be T
0.
minus, no, 0 to I understand. You have to solve it. And then you have to find the
T minus A11 into T minus A22.
Yeah. Into
Minus
1.
A12 into A21.
So T into A11, T into A22 minus A21, A22. What is this? T square minus A11 plus A22 T plus A11 A22 minus A21 A22. What is this? And I will set this to 0 or not to get the eigenvalues. So the roots of this equation will be, roots are the eigenvalues, right? Agreed? That's what you will solve this polynomial and get the eigenvalues. The roots are the eigenvalues. So do you see the sum of the eigenvalues are equal to the trace of this. And the product of the eigenvalues is equal to determinant of A. We'll show this formally also. Give me some time. Is this clear? For a polynomial? Yeah. So you have a polynomial. The solution to this polynomial is the solution are the eigenvalues. So the sum of the eigenvalues will be equal to the trace, and the product of the eigenvalues will be equal to the determinant. That's good. One more thing you can know from this. Can you tell me? So your polynomial, also known as, we can write this as PA of t, or the characteristic polynomial. What will be the degree of the polynomial? So for A being a n-dimensional, why I wrote that, you will see now. A is a n by n matrix. What will be the determinant degree of this polynomial?
Uh, मतलब dimension of the matrix.
Correct.
And
So you will see t minus 1, 1 and so on, t minus a n n, and all these terms will remain the same. So you will be left with some summation of, so t to the power n, we'll see this minus trace of a t to the power n minus 1, and then you'll have a bunch of terms which does not have a closed form, and at the end you will have a determinant of a, right?
yes.
Which will be the product of the eigenvalues. Good. So this will be what you'll be having. So what this can also be written as, do you agree this can also be written as t into minus lambda 1, t minus, I have written alpha 1, let's be consistent, alpha 2, and t minus alpha n. So any polynomial can be factorized if alpha I is to alpha 1 equal to alpha 1 and alpha 2 dot, dot, alpha n belong to complex numbers, right? All polynomials can be factorized. They have all polynomials have n roots or not? They may be imaginary roots, but they have n roots, right?
Yes.
So I can write this as n of these. So now say you have only k distinct alphas. So what will it be? So that's why I've written p minus alpha I equal to 1 to k ni, such that sum of ni is equal to n. We'll see an example, you'll understand. Do you understand this notation that what I am using?
Yes.
So there can be repeated roots. For example, t minus 2 whole square. Right? So you have all seen. So here the roots are 2 comma 2. So you will have, similarly, you will have a general formula for PA of t. And so for this case, Ni is known as the geometric or the algebraic multiplicity. Right? And we'll be seeing what exactly does it mean. Just some time. So now let's do a simple question just to motivate how cool this properties of eigenvalues are. Say p lambda, show that p lambda comma x is an eigenpair for a polynomial of A, where p is any n degree polynomial and lambda comma x is an eigenpair of A. So how do I do that? Any idea? So say pt. So let's write pt is an n degree polynomial. So pt I can write as ai t to the power n, or I equal to 1 to n. Yes or no? Or 0 to n, sorry. So any k degree polynomial can be written as this way. Do you agree? Now, if I write p of a, what will it be? it will be a matrix polynomial, right?
Yes.
So I have told you that ax is equal to lambda x, right? I have told you a lambda comma x is an eigenpair. So if it is an eigenpair, x equal to lambda x will hold. This is the eigenvalue, and this is the eigenvector. So if I multiply x on both sides, what will I be getting? This is exactly like the Fibonacci term, right?
Yes.
So what will I get? AK. What is a square x? Equal to lambda times. Tell me what is a square x? Is a into ax, right? This is equal to lambda x into a, which is equal to
Yes.
lambda x, which is equal to lambda square into x, right?
Yes.
So your a to the power nx is what? Lambda to the power nx.
Yes.
So do you see that you get lambda to the power n? X? Yes or no? This is the equation you will be getting. What n I have written? K. Right? So this is what? Polynomial of lambda from definition of the polynomial. Yes or no?
Yes.
So is what equation did I get? PA of x is equal to P of lambda into x. So is P of lambda comma x a eigenpair or not? So it's like this is an equation, right? So it's a bx is equal to some b tilde x. So it's an eigenvalue, eigenpair, eigenvalue, eigenvector equation. These two are the same, right? And this is a scalar. I hope it is clear. If it is not, you stop me. I'll wait for couple of seconds and then I'll go to the geometric and algebraic multiplicity. All right, it's clear to
Dada,
you.
could you explain how how is this working? How is this lambda square being replaced? Like, what is the geometric meaning basically?
In which case?
For eigenvalues and eigenvectors, like ax equals to lambda x, what does this mean actually?
That's why I was telling you in the beginning, right? So
Yeah.
what is ax? Ax is a vector, right?
Yes.
X is also a vector.
Yes.
So I am saying, and lambda is a scalar, right?
Yes.
So the right hand side is a scaled version of the vector, right?
Yes.
So I am saying, what does matrix A do to the an eigenvector of a matrix is only scaled by the matrix. So the matrix cannot rotate it. Normally, your matrix, your vectors can be rotated, right? And then scaled.
Yes.
Because when you're multiplying two vectors, you have one vector and you in the column space, your resultant vector can be somewhere here. Right?
Yes.
Your ax can be somewhere here. But eigenvectors are so powerful. At least if you sometimes wish to study quantum mechanics, you'll see eigenfunctions also. So they are so powerful. Why? Because this will not be scaled at all. It will not be rotated at all. It will only be scaled by the matrix. And they are fixed for a matrix, as we have seen if by solving ax equal to lambda x. Right?
Okay, so the eigenvectors are a subset of vectors
All
from the
vectors.
column.
Yes,
Okay.
from the columns, from the row space, right?
Yeah, row space of A.
Ax is whenever you multiply exactly row space of A. So such that they will be so that you can write any vector And row space and column space are the same. Don't confuse yourself. So
Yes,
A
yes,
is
yes.
n cross n. So row space, column space are the same. So you can write U0 as any sum of any, as you saw here. U0 as any sum of any two eigenvectors, right?
Okay, okay, understood. Yes.
So row space and column space are the same. That's why it's only defined for square matrices. Let's see geometric multiplicity now. So if you have, so you can see that you can have repeated eigenvalues, right?
Yes.
So this is the equation that we had. Thus that all the ni's would sum to n, right? For a is n cross n, right? So all they will be summing to n. So these ni's are the algebraic multiplicities. And now what is the geometric multiplicity? See, we will solve a question tomorrow very clearly. You'll be seeing, I'll show you like diagonalization now, and then you understand why is this very, very bad if you have a poor or a defective matrix. Then all your hopes of using the eigenspace is reduced to sham. So once you see, there are two things I told you in all of linear algebra. One is the column spaces and one is the energy of these. So column spaces, eigenvalues are related to the column space only, right? They are those vectors that keep yourself on the column space, on the same, not only on the column space, but in the same line. So now you see, so if you have, say, AX, so AX is equal to AX1 is equal to lambda x1 and AX2 is equal to lambda x2. So what is the number of vectors in the uh, for a particular lambda here? Can you tell me? For a particular lambda, say x1 is not equal to x2. So what is the number of vectors? So there are two eigenvectors, right? Two eigenvectors for one eigenvalue, right?
Yes.
And this can only happen when, can you tell me? When can it happen? This is one of the favorite questions of profs if you are going to apply for interviews. So when can it happen? So I'll subtract, say, ax minus lambda x. What will I get? A minus lambda I x, right? Equal to 0. Yes or no?
Yes.
So A has to be multiple dimensional. So your null space of A minus lambda I is at least greater than equal to 2. Right?
Yes.
That's why you got two vectors which are independent. Right? Two independent vectors means what? Your null space must have two vectors, two components. Right? So for the single eigenvalue, you will be ending up with a combination of all these are eigenvalues. Yes or no? If you have, if an eigenvalue has multiple eigenvectors, the combination of all those eigenvectors will also be a eigenvector. Yes or no?
Yes.
So if you multiply ax tilde, you will get, what will you get? Ax1 c0 plus ax2 c2. What am I going to get? Lambda 1 c1 x1 lambda 2 c2.
Yes.
Not lambda 2, only lambda, because I've said they're the same. So you'll get lambda c1 plus lambda c2 into, what am I writing? C1 x1 plus C2 x2
Into
into
lambda.
lambda. Correct. So C is again an eigenvalue. So if you have many dimensional, so for a particular eigenvector value, you can have, say, k dimensional eigenspace. So you will have a k dimensional eigenspace, and all of them will be eigenvectors to the matrix. So that's how is defined a geometric multiplicity. So geometric multiplicity of a eigenvalue lambda will be the space of null, the null space of A minus lambda I. Is that clear?
Yes.
So you have 2 here, so it's a 2-dimensional space. Agreed, Ritik? Mujid?
Yes, the null space. No?
Yes, so the null space will be equal to the number of eigenvalues, eigenvectors corresponding to the eigenvalue. See, now I'll show you a defective case. Look at this eigenvector. Look at this matrix. So what can you say from this matrix? For a defective matrix, this algebraic multiplicity will be more than geometric multiplicity. I'll show you just now why it is true. But before that, tell me, what are the eigenvalues for this? Just seeing them and tell me. Lambda will be what are the eigenvalues? What is the characteristic equation of A? Determinant of Ti minus A? Give me a
T
second.
minus 1 whole square.
T minus 1 whole square into T minus 2, right? This one. The first matrix.
Oh, okay. Okay.
T minus 1, T minus 1, T minus 2. Determinant of this will be T minus 1 square into T minus 2, right?
Yes.
So for a
Yes.
diagonal
Yes.
matrix, the eigenvalues are at the diagonal. Or for an upper triangular matrix also, the diagonal, do you agree it will be the same? Upper triangular or lower triangular? Why, can you tell me? For the upper triangular matrix, all the eigenvalues are at the diagonal. Any idea? So say you have T11, T22, Tnn, and everything below it 0. And you do lambda, minus lambda, minus lambda, minus lambda, right? And you have something star over here. So what is the determinant of this? Tnn, if I expand with respect to this, so I will get Tnn minus lambda into determinant of this, right?
Yes.
So determinant of T11 minus lambda, T22 minus lambda dot 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 T n minus 1 into minus lambda, right? This is what you will get. Others are all 0 in the denominator in this column.
Yes. And
So
similarly, it will become the product
similarly,
of
it will
the.
follow. Exactly. So it will be the product of Tii minus lambda I equal to 1 to n. So this is a very important property to know, that if you can make an upper triangular matrix from any matrix, you can find the eigenvalues. We'll see finding eigenvalues can be very simply done by similarity transformations. We'll see in 1 second. So you have this equation, right?
Yes.
So your lambdas are 1, 1, 2, correct?
Yes.
So if what is A minus 1 into I? A1 into 1 into I? 0, 0, 2, 0, 0, 0, 0, 0, 0, right? Yes or no?
0, 0, 1.
Oh, sorry. Yeah. 0, 0, 1. I'm subtracting A1 minus I. So what is the eigenvalues, eigenvectors? or the null space of this. So you have to find the null space of this. Very simple. This is the only pivot or the dependent column. So you can do whatever you like with these two. So do you agree? 1, 0, 0 and 0, 1, 0, 1, 0 are both eigenvectors? Or both vectors in the null space. So you multiply 1, 0, 0, you'll get 0, and 0, 1, 0, you'll get. So any combination of these two will be in the null space, right? Of A minus lambda I, or your 1 lambda equal to 1 has geometric multiplicity equal to 2, right? 2 basis vectors. In the geometric space, you have 2 basis vectors. What does 2, how many eigenvectors does 2 have? A minus 2i is minus 1, 0. What should be the eigenvector of this? Or in the null space, vector in the null space? So A minus 2i into y should be 0, right? So what should be y? I've shown you yesterday what to do. These are the pivots. So in the pivot, I'll be putting these are the independent or the dependent variables, right? This is the dependent variable. So what will I do? If this is my I, this is my f. This, right? So I'll just put wherever you have dependent variables, I'll put identity, right? I told you yesterday. And the rest will be in the remaining two. So 1, 0, 0. Right? I have only zeros here, 0 to play with. So I'll put zeros on the top. So is 1, 0, 0, 1 eigenvalue or not? Minus 1, 0, 0, 0, 0, 0, 0 into 0, 0, 1. Is it a, what is the product?
0.
So does this 0, 0, 1 belong to the null space of A minus 2i or not?
Yes.
Just practice how to find this eigenvalues. You have to practice it. Otherwise, it will be very, if it's a very simple matrix, it will become very complicated if it is a much complex matrix. So what is the lambda equal to 2 has a geometric multiplicity of 1, right? Only one eigenvalue, eigenvector, yes or no?
Yes.
Okay. So, but there can be cases where your life will be very difficult, like this. What are the eigenvalues of this? A2 equal to 1, 1, 1, 0. I told you already, the eigenvalues are sitting on the
Diagonal. 1 and
correct.
1.
Lambda is 1, 1. So what is A minus I? So Ax is equal to x, right? 1 into x. So it's A minus I into x is equal to 0. So what is A minus I? 0, 0, 1, 0, right?
Yes.
So for this, what is the eigenvector or the null space of this matrix? There's
0,
only
1.
one. 0, 1. There's only one pivot. So this is one dimensional null space. Do you agree?
Yes.
Not 0, 1, 1, 0, right? One null space. So this is your f. So in place of f, this is your pivot. This is your independent vector. In place of the independent vector, I will put these vectors f. I'll put minus f. And in place of I, which is this, place of f, I'll be putting I, right? So 1, 0 is the eigenvector. 0, 1, 0, 0 into 1, 0. What is this? This is 0, 0? Yes or no?
Yes.
Correct. So just recall, okay. So this is your pivot, right? Yesterday I told you.
Yes.
So if this is your first non-zero element, it's a pivot. So I told you to treat them as your independent vectors. Agreed?
Hmm.
So this is your I. This is your dependent vector, which is f. So in the vector, what did we write? We wrote I in the place of minus f in the place of I. So I is corresponding, f is this, right? Corresponding location.
Yes.
And f, I wrote I. So I wrote 1 in case of this and 0 in case of f. So I got 1, 0. So do you see the null space of this is of A2 minus I is only one dimensional? Right?
Yes.
You have one vector in the column space. So this is known as a defective matrix. So your geometric in this case for A2 equal to 2 and geometric multiplicity equal to 1, right? So in this case, what we will be doing next is not going to be possible, which is also known as diagonalization. So we'll be doing that, and that will be the last thing we'll do. Before doing what is diagonalization, I'll be showing you what are called similar matrices. Then you'll understand what is the. So this is the axioms or the property of a similar matrix. Similar matrices are matrices that can be written in this form, where B can be written as S inverse AS. What does it mean? It means given a matrix, a full rank S matrix, so your A and B are both n into n matrices. So why am I doing this? So if you can write B as S inverse AS, what will be the use? It will be useful in many ways. It will be useful because
If
yeah,
we give some power to B, then automatically it will be equal to S
exactly.
inverse
And
A.
so exactly. So B, first thing, B to the power n is equal to S inverse A to the power n S, right?
Yes.
Others? That is also a thing. Useful because B and A have same eigenvalues also. So do you see, now you will see the field root factor. So if I'll show you why they have the same eigenvalues. But once you see that they have the same eigenvalues, what will you do? You will convert any matrix to this form, and you will be converting it to a diagonal matrix or an upper triangular matrix. If S is easy to find, assuming this is easy, if you can't find S, they have the same eigenvalues. So it is equivalent to finding just these diagonals will be the eigenvalues of A. Yes or no?
Yes.
Eigenvalues of A, which will also be our eigenvalues of B. Now I'll show you what is the property that you have. The property would be show that for the similarity, it's the equivalence relation. So people who are preparing for GATE and all, this property you have to do first order logic things, and this is one of the things that you have to show, that equivalence relation. What does an equivalence relation mean? It means it is reflexive symmetric and transitive. What does that mean? Again, why am I saying, why is it important? So it means that a relation R to a relation x comma y is symmetric. For being equivalence, it will hold all beautiful properties. So if x comma y belongs to the relation, y comma x will belong to the relation, right? Similarly, x comma x will belong to the relation. Similarly, there will be properties like this: x y belongs to the relation, y z belongs to the relation, and x z will also be belonging to the relation. So this is a side detour, but this will give you good group characteristics because you'll be closed within those space and you'll be able to do transitive operations one after the other. So how can I show reflexive? Can you tell me? A is similar to A. How can I show? Reflexive will mean A is similar to A, right? How will I show that? Very easy. I can write A as A I inverse I or not. I is just identity matrix. So inverse is easy to find. So A is similar to B will yes. So now only I've started mixing up rotations because this helps you. This equivalence relation will help you in getting that. So you tell me, what will I do next? So how will I show that B is similar to A? A is similar to B means this, right? How will I convert to B is similar to A?
We multiply by S and S inverse both sides.
So A, correct. So if I multiply this way, I'll get S inverse. So I'm doing it once. So it will become I'll be using it continuously throughout next. So this will become I, this will become I, this is becoming I. So A is B S inverse, which is also similar. So B is similar to A. So transitive also similarly you can do. So A can be written as S inverse BS, and if A is similar to B, similarly B is similar to C means B can be written as some S2 inverse C S2, right? Agreed? So what can I write this? I can put this value over here. What will I get? A is equal to S2 inverse C S2, right? So it is S2 S inverse C into S2S, correct?
Yes.
So these are similar. These are, if I replace this as some W, this is another W. So I'll get WCW. So why is this so important? So we'll show that now, which is because they have the same eigenvalues. So we started 10 minutes late. It's all 10 minutes are left even today. So its recording is 220 minutes. So after 10 minutes, it will be, I'll be also taking, let me see how much time. Yeah, it'll be over by 5:45. Okay. So tell me, how do I do this? To show that A and B have the same characteristic polynomial. Means, do you agree if they have same polynomial means same eigenvalues? Yes or no? This will be used throughout. We'll be seeing singular value decompositions and so on. There also it will be very important. So pay care, pay attention. Same eigenvalues. Do you agree? Same characteristic equation will mean this. Characteristic equation is nothing but what? pi of t minus alpha is, right? This is what we said. Let there be some repetition, no problem. Right?
Yeah.
So if it's same for two matrices, will mean so alpha is are the eigenvalues, right?
Yes.
Now let's see. So PA of t, what is it? Determinant of Ti minus A, correct? Next, how I have said A is similar to B. So how will I replace this as S inverse BS? I can write for some S
Yes.
Ti. Now pay attention. I'll do a trick, magic. I can also write S inverse S here, right?
Yes.
Why can I write that? Because this is an identity matrix and this is a scalar. So identity into S is S and scalar can be moved out. So it's still equal to Ti, right?
Yes.
So now what will I do? Can you tell me? Very simple thing I'll do now. Determinant of S inverse T minus B S, right? So what is the product of determinant of product of two matrices? Right? We all know this from our school
Yes.
days. So what will it be? Determinant of S inverse determinant of Ti minus B into determinant of S. So what is determinant of S inverse?
1 by
One by
determinant of S.
1 by
Very good.
determinant of S.
Yes. So this is 1 by determinant of. So I can cancel this and this. So do you agree that this is equal to PB of t? They have the same characteristics polynomial.
Yes.
So now A and B will have the same eigenvalues, right? Yes or no?
Yes.
Good. So but converse is not true. How will you show that? We'll see this after diagonalization. We'll do diagonalization and then everything will fall into place. Yeah. Let's do diagonalization. So what does diagonalization say? So if geometric mean is equal to algebraic mean, what mean I'm saying? Multiplicity is same for both geometric and algebraic. Then we can, then A is similar to a diagonal matrix. This is what I was saying, like, right? I was giving you the motivation. Why am I studying similar matrices? If A has distinct eigenvalues, values or geometric multiplicity of all lambda equal to algebraic multiplicity of all lambda, then A is similar to a diagonal matrix such that diagonal matrix is lambda 1, lambda 2, lambda n. Right? What are lambda 1 to lambda n? These are the eigenvalues. If you have understood, I'll show you how, or if you have not, the motivation, I'll tell you the motivation again. Is the motivation clear? So what I am saying is, if I know that a matrix is similar to a diagonal matrix, I can just use these as the eigenvalues of A. Yes or no? So diagonal matrices will have the same eigenvalues, right? Diagonal matrix will have eigenvalues are same as the diagonals. So I'm saying if they are similar, so lambda will definitely contain the eigenvalues of A or not? Because they are similar.
Yes.
Is the motivation clear? So why will lambda contain the eigenvalues? Because they are similar, right? I have an S inverse. S lambda S inverse. So I'll show you how is it done. Very simple. So AX is equal to, say, AX1 is equal to lambda 1 x1. Since we have said geometric multiplicity is there, so this will be, there will be n equations or not. Since we have no bad behaved eigenvector that takes up two values, right? As we showed in that 1101 case, right? In this case, we saw that only one eigenvalue was there, which was taking up both the eigenspaces. But here I have said geometric multiplicity is same as the algebraic multiplicity. So there is no question of taking up the entire space. Agreed?
Yes.
There are n eigenvalues. So do you agree? So if I stack a x1, x2 dot 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 xn, these are the eigenvectors like this, which are independent, of course, because by definition eigenvectors will have to be independent. Otherwise, they are going to be, they will not have any equations. They will be mapping to some other space like that. It happened here. In this case, if they're not independent, this like similar case will happen. Now I will write it as lambda 1 x1, lambda n xn. Yes or no? I'm just stacking them one after the other. So this is also equal to what? Lambda 1, lambda 2, lambda n, 0, 0, and x1, x2, xn or not? Or rather, no. x1, x2, xn. Is it? No. x1, x2, xn, right? See, the first column times this. So lambda, it becomes the lambda 1 x1. In the last case, last column times this lambda n xn, right? Yes or no?
Yes.
Yes.
So if I write this as S, so I will get AS is equal to S into lambda, right? So which means A is equal to S lambda S inverse. We'll do a question in this of this in the next day, how to do the factorization by hand. But anyways, this will exist, right? If there is it is not a defective matrix, it will exist. We agree to that. Okay. So now we'll be seeing the converse is not true. How can you say the converse is not true? That what converse of this is not true, which means you have same eigenvalues. Doesn't mean A is similar to B. How can you show that? Can you give me two examples? Counter example is enough to show this. How do I show that? So let's say A is equal to, I have given you the hint already, and B is equal to 1, 1, 0, 0. What are the eigenvalues of B? 1, 1. A is, we have already seen 1, 1, right? Any doubt?
Yeah, no.
So are these two similar matrices? And how can you say they are not similar? See, this is I, right? Yes or no? So if this was similar, so I could have written some S, A S inverse as equal to I, right? Yes or no?
Yes.
Yes.
Because this is the diagonal matrix of its eigenvalues. Diagonal matrix of A's eigenvalues. But alas, you can't do that. Why? Because S has only one x1 that is equal to what? 1. So S inverse does not exist. Is the understanding clear? So you have only one solution to Ax equal to lambda x for a vector, although this has 2 as the property, 2 as its algebraic multiplicity. There exists only one x, right? So in a defective case, it doesn't mean that having the same eigenvalues will mean they're similar or will have, yeah, they're similar. Do you understand? Or do you need anything that is not clear? So S inverse, there's no question of an S inverse because this S matrix has to contain all the eigenvectors, right? And there's only one eigenvector, so you cannot construct a matrix. Yes or no? Is it clear or not? Or then, if it is clear, let's see the last two theorems and then we'll stop. Have I completed everything? Yeah, I have to show this theorem also. Let's see this. So how will you show that algebraic multiplicity is always greater than equal to geometric multiplicity? Very short proof, can you tell me? We have done so if lambda is repeated k times, how many eigenvectors will it contain at max? It will be k, right? We'll show that. So let's say lambda, let's say geometric multiplicity of x is k. So then what can I write? If I say that the geometric multiplicity of lambda, of our eigenvalue is k, what can I write? What does it mean? This will integrate everything in your brain. So that's why I'm asking. It means there are k equations like this or not?
Yes.
There are k independent eigenvectors, right? That's geometric multiplicity, null space of A minus lambda I. Yes or no? X1, X2 belongs to null space of A minus lambda I, right?
Yes.
So what can I write? I can write A x1 xk and then some other xk plus 1 x plus k plus 2 to a k. So I will create an S like this. S will be equal to x1 x2 xk, and then I will be having k plus 1 till n such that S is invertible, right? I can always do that. If this is independent, I can get the rest of the basis vectors by augmenting. Do you agree? So what will be AS? Can you tell me? AS will be, so for the first k elements, it will be lambda or not. These are all the other eigenvalues. Even if they're not eigenvalues or null space, whatever, at least k of them will be lambda. Yes or no? And here I will have S. If it is not clear, you ask. I'm just writing this in form of an equation, right? And I can have something here. This will be 0. And then we have some C matrix, right? So first k elements will be like this. Right? You can put it this way as well. So because you have AXI, so if you write this equation S here, so first k columns must be AXI equal to lambda xi, right or no?
Right.
So I'm not worried about the other columns. Do you see? The first k columns below nothing will be there. Do you agree? Because first k columns will be AXI equal to lambda xi.
Yes.
Yes or no? So there will be nothing below. Whatever is here, I am not worried about. Do you agree?
Yes.
So I can write, and I have set S to be invertible, so I can write AA as S lambda ik AC 0 S inverse. Yes or no? I can write this. Ik means an identity matrix of size k. Right? It's sort of half diagonalization. Yes or no? I hope it is clear. So what will be the characteristic polynomial of A will be same as, if we name this as some lambda. Again, yes or no? So I've shown you, right? So that any is similar, like A is similar to lambda. So what will I get? Is it not clear? Is up to this it was clear, right? So now what is my argument? Is that not clear? We showed this theorem, right? Just now I proved it. Where is it? Similar matrices have same characteristic polynomial. We showed, right?
Yes.
Okay, if you're not clear, you stop. Okay. So they will have the same characteristic polynomial. What is the characteristic polynomial of lambda? Can anyone tell me? Determinant of pi minus lambda, what will it be? Do you agree it will be t minus lambda to the power k determinant of C? Right? So I will be expanding into this. So I will have a determinant of this term into determinant of this term, right? Yes or no?
Yes.
So you see the algebraic multiplicity of lambda has to be greater than or equal to k, right? At least k times I've already got here. So which will be greater than or equal to geometric multiplicity of lambda. Is that clear? So if it's I think you are not being able to follow anymore. So we'll do the Cayley Hamilton theorem next day. So it's not very long. It's 2 lines. Do you want me to do it next day, or do you want me to finish it? It'll take 10 minutes, or if you want, we'll stop. And it is better that you ask me question about this. This is more interesting than doing that, which is very simple. Is it okay? Ritik, I think you did not understand. Tell me what is not clear. Will not do the Cayley
The diagonalization part, I think I'll have to study once more.
So
After that, I will.
Okay, saying so this one, right? So diagonalization, I'm just multiplying the eigenvalues, right? Eigenvectors. If I multiply the eigenvectors, I'll get these equations, right?
Yes.
For all the n of them. So just follow me. I'll give you step-by-step cues. You will just have to parse that. So I can write all these one equation like this. Do you agree? Because
Yes.
this is where you are having the problem, right? So a x1. So if I write that, what will I get? Lambda 1 x1. That much is clear.
Yes.
Now, instead of one column, I can have two columns, and the same thing will. I will stack the columns like this, lambda 2 x2. Yes or no?
Yes.
These are all column multiplications, right? So just think the first column is not there now. So you will take the linear combination of the second column, and there is some x2 equal to lambda 2 x2, right?
Yes.
Now is this making sense?
Hmm.
So if you have n of them, so you can stack one after the other, so you will get this equation. Now this is clear.
Yes.
And then, of course, if this is true, so you will just lambda times x1, lambda 2 times x2. What does it mean? So there is a diagonal matrix where with scales only the columns, right? Yes or no?
Columns.
See,
Yeah.
there is
Yeah.
all zeros below. So you all the other columns will be 0. Only the first column will be lambda 1 times x1.
Yes. Yes.
So now you can use the same logic here. So you'll have k of these, which will have 0 below, right?
Yes.
And the rest is there. I don't
Rest
care
will
at all.
be.
It's not my money. Little bit of a worry also. Yes.
Hmm.
Rest is not my worry because I have shown that A is similar to this matrix. If they are similar, they will have same characteristic polynomial.
Yes.
Yes.
And then if they, what is the determinant of t minus this? So you will have to this is the diagonal matrix. It will have this determinant, right?
So could you repeat
Respect
that?
to
You
this
got.
block. With this block, if you yeah, I'm telling. So I will tell you what is the was the last question that 1 minus lambda t minus lambda k times, right?
Yes.
And you have 0 here, you have a here, and you have
Oh.
b here, right?
Huh.
What is it? You keep expanding about this, no problem,
This will give us
isn't it?
t minus lambda to the power k, which is k times.
Exactly, t minus lambda to the power k. See, because a's will all go to 0 because of this.
Yes.
When you do, you will hold all
Determinant of.
of them. B. So t minus lambda to the power k will into determinant of b, which can have more lambdas, right? More can have more t minus lambda. Stopping it to have. So the algebraic multiplicity of lambda has to be greater than equal to k, right? Which is we have taken as geometric multiplicity of lambda. Clear?
Yes. Yes.
The last. Good. So see, this you had in school only. You can will do it next day. Used to this question used to come in your ISC exams that find the inverse given this matrix. So we'll do something called hardly take 5 minutes. So 10 minutes will be required next day. We'll do it. I'll introduce what is called a Schur's triangularization next day. And I have not shown what is left. This is left also. So 15 minutes will be required next day. I'll have to show that this is true for any A, right? So any n-dimensional A will have the determinant at the end, we'll show it using Schur's triangularization. So before we stop, I will just introduce Schur's triangularization and we'll stop. We'll not do, just so that you can parse this while you are away and we meet middle of next week. See, so if we have A equal to, so Schur's triangle, we are not going to prove Schur's triangularization. Is not, you require at least a month background. We'll have like one thing is there called householder matrices. I have given you the enough background. You can go and see the house matrices and derive the Schur's triangularization. But we'll be using Schur's triangularization always because there's nothing very difficult in this. It's just a construction, but it will take 1 full 2 hours to do it. So I'm going to skip it. Do not have that scope. That's why. But if you read it, we can do it at the end someday, right? When we have all completed all the assignments and all the other things. So what is Schur's triangularization saying? It says that any matrix A, which is n by n, can be written as, this is also a very, very useful thing, as A is equal to U Hermitian T U. What does that mean? Where U Hermitian U is equal to I. What does that mean? U is a orthonormal matrix, right? It's called a, you have studied orthonormal matrices, right? Where U transpose U is equal to I. What is U transpose U? A1, A2, AN, and A1, A2, AN. So if it is I, what does it mean? Let's write U. U1, U2.
Its own inverse.
Inverse.
Youth. Exactly. This is U transpose is equal to U inverse. When can it happen? Only if and only if UIs are all orthonormal. Right? See, U1, you multiply this, you get, what will you get? 1, 0, 0, 0, right?
Yes.
So what is U1 transpose U1? 1, right? Or orthonormal matrices, orthonormal vectors. Orthogonal vectors, what is it? You agree to this? Uy into uj is equal to 0.
Yes.
If uy perpendicular to uj. So all are perpendicular. So this is 0 if I not equal to j and 1 if I equal to j. So which elements will be only 1 here? I1, this is going to be 1. U2 times U2 will be 1. Similarly, UN times UN will be 1. Rest all will be 0. Do you agree?
Yes.
Good. So this is also, do you see, this is also a S inverse TU or not?
Yes.
Exactly. So this can be, this is also similar, right? A is similar to T, and this is called unitarily similar, which is even a better case. Unitarily similar means you don't even need to calculate inverse. Inverse calculation is very difficult, right? Ritik, yesterday we did, is ON cube. Elimination has to be done. But transpose is only ON operation. And computers, if you have linked lists and all, you don't even need the operation. It's just O0 operation, O1 operation. So this is even better. So if you will see how it is useful in PCA, we'll give you PCA, another machine learning application of matrices in the next class. And you'll see how having these matrices are useful. But tell me, one of you, how? So if you have a triangular matrix, so T will be something like this, where T11 till Tnn. So Tii will be lambda I. Okay, where lambda is the ith eigenvalue. Okay. So you will be A is always can be written as a similar matrix. So even if you cannot diagonalize it, you can always write it as S inverse TU or U inverse U Hermitian TU. If you cannot diagonalize it, the rest will always all be zeros, right? So all the unique eigenvectors will be there. So if it's in a rank R matrix, how many eigenvalues will you have? Rank R matrix has how many eigenvalues? How do you say that? So AX is equal to lambda X, right? If A is rank of A is R, what does it mean? What is the dimension of the column space of A? N minus R, right?
Yes.
So how many solutions will you have to AX equal to 0? Rank is R means you have said yes. Dimension of null space is N minus R, right?
Yes.
So how many solutions to this? How many basis vectors?
N minus R.
N minus R. So you will have N minus R zeros, right? So everything. So what am I trying to do by showing you everything? I'm proving each and every statement to you. Why? Because I want you to inculcate this habit, not believe anything until you have proved it mathematically. Okay. So we'll stop here. Just look at the Schur's triangularization, what I have said here. So any matrix can be written as S inverse TS, where T is having diagonal matrix containing this eigenvalue. So diagonal matrix is as good as a triangular matrix is as good as a diagonal matrix, right? For all the purposes that we need it to. So I'll stop recording. And if you have any question,